Hey guys, today we are doing 3.2 notes, which is all about complex numbers. So yesterday in class we saw, or I guess yesterday in the notes, we saw a problem where we tried going through and solving using square root method, and we ended up getting a negative number underneath our square root, which meant we had no real solution. And in order to kind of figure out a way that we can still describe those solutions, because even though there's not a real number that works in that equation, there are still applications and benefits to knowing what ways of describing those solutions. We have a new number system we call the imaginary numbers. And we indicate we have an imaginary number with the letter I. So I'm going to go ahead and zoom in here. I is the letter that we use to represent an imaginary number. So we know that we can take the square root of positive numbers like 9 because 3 equals 3 because 3 squared equals 9, but technically we know that the answer will be plus or minus 3 because both positive and negative 3 squared would give me positive 9. In this case, if we try taking the square root of a negative number like negative 9, we can't do that because there's no number multiplied by itself, no number that's squared would give you that negative. So it has to be either 3 times 3 equals 9 or negative 3 times negative 3 equals 9. So that's just, again, why we can't take those negatives. However, we will be experiencing some things where here we'll add in that I to represent a square root of a negative 1. That's what that I represents. That's what allows us to be able to simplify a square root that has a negative involved in it. So I just represents a negative square root, which means if I is the square root of negative 1, if I squared that number, I'd end up with just negative 1. So what we're going to go through today first is just kind of explore these ideas of imaginary numbers, being able to simplify negative square roots, and then we'll get into some problems where we're solving involving negative square roots. So kind of where those get applied. So first and foremost, simplifying the square root of a negative 121. Here, I can't simplify the negative square root of 121 because it's negative. But if I apply my rules of square roots, I know that I can rewrite anything that's underneath my radical as the product of two radicals, as long as those two things multiply together to give my original thing. So here, what I could do is split this up into the square root of negative 1 times the square root of 121, or vice versa. Actually, probably would do the other way around here, where I'd probably write it as 121 times the square root of negative 1, because now I can simplify each of those. I know that the square root of 121 is just 11. We just identified that I represents the square root of a negative 1, which means here this simplifies down into just 11i. That's what the square root of 121 is. You can do the same thing with the square root of negative 28. It's just that you're going to still have some stuff left over from radicals, because if we were to look at this originally, if we didn't have the negative there, 28, if I'm trying to find the square root of that, I would break it down into the biggest perfect square and whatever my leftover is. So in this case, 4 is the biggest perfect square that goes into 28. So the way that I'm going to split this up, I'm going to say the square root of 4 times the square root of 7. And then I also have, giving away the answer there, square root of negative 1 as well. That's what I'm going to split it up into. So from here, this and this simplify into outside my radical, because the square root of 4 is just 2. The square root of negative 1 is I, and then my square root of 7 stays as is. So that's what that would simplify down into. Now, if I'm given something that has I involved in it, you treat that just like a variable. We can just leave it in terms of I. So here, 5 times 2i would just be 10i, and that's it. Nothing else funky happening to it, just like if it was 5 times 2x, it would be 10x. Where it gets to be a little bit unique with the multiplication of two imaginary numbers. So here, 3i times 2i, just like I would do, again, if this is a regular variable, coefficients get multiplied, so negative 6, and then my variable gets multiplied together to give me I squared. However, if you look above over here, we said that I squared was negative 1, so I just have to make sure I do that substitution, where here we know that this is negative 1. So negative 6 times negative 1 means negative 3i times 2i is positive 6. Okay, So a complex number, so where these come into play, where these imaginary numbers come in, a complex number, just like it sounds, it's complex. It's made up of a combination of both a real number and an imaginary number. And it's always in this format, a plus bi. So here a and b are going to be numbers. I obviously is there to represent the imaginary portion. So a would be the real part of my complex number. The bi would be my imaginary part. So here, like I just said, it's separated into imaginary and reals. When you have these, you can, and we're trying to combine them together, you treat it just like if it was a regular algebraic expression. You keep your real terms and your imaginary parts separated, just like you keep your like terms separated. So if I'm adding negative 2i, there's negative 2 plus 5i with 1 minus 7i, your like terms would be your negative 2 and your 1, so that's negative 1. And then your 5i and your negative 7i makes a total of negative 2i, just like if I was collecting like terms. So adding those two complex numbers together gives me that. Here, if I'm subtracting, I have to make sure that this gets flipped, because if I'm subtracting, the second parenthesis has to change my signs. So now 4 and positive 1 gives me 5. 6i minus 2i would be a plus 4i for my final answer there. Okay, moving along. If we multiply two of them together here, just like you would expect, if we're treating it like a regular algebraic expression, we're going to FOIL these together, or I guess you could do box multiplication if that's something you're more comfortable with. I can do one of each just to kind of show you how it works there. Here, the only thing you have to be careful of is once you've combined your like terms, once again, we have to make sure we do that substitution to do I squared with negative 1. So here, I'm going to go ahead and do this first one using FOIL. So again, FOIL meaning first times first is 18. Outsides would be negative 6i. Insides would be 36i. And then my lasts would be a negative 12i squared. So I'm going to do kind of, well, I'll show you both. So here, adding up my like terms, because I have two I terms. So 18 plus 30i minus 12i squared. Now again, we have to make sure we can't leave I squared as is, so I've got to make that substitution for negative 1. So this becomes 18 plus 30i plus 12, because negative 12 times negative 1 would be positive 12. So 18 plus 12 is 30 plus 30i. Now usually when I do this, these two steps right here, I'll combine these two steps together, where I combine my like terms for my i's and also substitute negative 1 for my I squareds, just to save a couple of extra steps. But as always, personal preference and whatever you're more comfortable with. For this other one, if you want to do box multiplication too, you could. Here, if I make my little box, don't know why it made it so small, but that's okay. So 1 plus 4i, 3 minus 6i. So here that we multiply to get 3, 12i, negative 6i, and then negative 24i squared. So collecting up your like terms, 3 plus 6i minus 24i squared would give me, but that would be my expression from collecting my like terms from my box. And again, I just have to make sure I do this substitution here for negative 1 in here for I squared. So 3 plus 6i plus 24. So I get 27 plus 6i for my final answer. Okay. So second to last part here, solving complex equations. For solving complex equations, again, remember, my real and my imaginary parts have to stay separated from each other. So if you have an equation that involves complex numbers, there are two complex numbers setting equal to each other, because my reals stay separated from my imaginaries. If I have two complex numbers that are set equal to each other, that means the real part and the real part have to be equal to each other. The complex part and the complex part have to be equal to each other. So all you're going to have to do is set your real parts equal to each other and your imaginaries equal to each other. Imaginary. So for this first equation over here on the left side, 4x plus 3i equals negative 12 plus yi, and we're asked to solve our equation for x and y. So here, these two parts that I just underlined, those are both my real numbers because they don't involve I. So they have to be equal to each other. 4x equals 12. So divide by 4, and x equals 3. Here for the squiggly underline, my two imaginary parts also have to be equal to each other. So 3i equals yi. I can divide by I on both sides to cancel them out. And I get y is positive 3. Now, for most of us, you probably don't need to write out all of those steps because these equations are, in general, usually pretty straightforward. But sometimes you might need to write it out if it's something more complex. Like here for this right side, for my two real parts, even though it's not always written in the same form. Usually it's real plus or minus my imaginary. Here it's a little bit tricky because my real parts are on the outsides. My imaginaries are in the middle. But that doesn't matter. As long as the imaginary parts are the ones that have I involved, the real parts are the ones that do not have any I's in them. So here, it's negative 7x and negative 21 are my two real parts. So negative 7x equals negative 21. And of course, when I divide by negative 7, I get x equals positive 3. And then really for my y value, I don't have to do any kind of work because if 23i equals yi, obviously y has to be 23. Okay, moving right along. For the last part, solving quadratic equations. So now this is where my i's get involved, where the problems that we saw yesterday are, bringing this full circle. Here, I'm asked to solve the quadratic equation, or sometimes it could be phrased as find the zeros. That means the same thing, solve the equation. So here, if I'm trying to solve 5x squared minus 20, 5x squared plus 20 equals 0, to solve that, I would start by getting my x squared term by itself. So 5x squared equals negative 20. I divide by, I'm starting to preview my answer here, divide by 5 on both sides. Those give me x squared equals negative 4. I take the square root of both sides. X equals plus or minus. Now in this case, I can simplify because even though it's negative, I know that just means I'm going to have an I for my answer. So in this case, the square root of 4 is 2, and then the square root of the negative gives me I. So here, I still have plus or minus because I'm still solving an equation in this case, just like if I was taking the square root of 4 on both sides, my x would be plus or minus 2. So here it's just that my x is plus or minus 2i. For the last one here, same process. I'm going to subtract 5 on both sides. 3x squared gives me negative 72. I divide by 3 on both sides. X squared equals negative 24. Square root both sides. X equals plus or minus. This one, 4 is my biggest perfect square. So the way that I would split this up is going to be square root of 6, square root of 4, and the square root of negative 1, if you want to write it all the way out. So here, my square root of 4 and my square root of negative 1 are going to simplify, which is 2i, and then I still have that square root of 6 left over to give me my final answer of x equals plus or minus 2i square root of 6. Okay, that's all I got for you guys today. Homework down there at the bottom is page 108. Sorry, I scroll up so you guys can actually see it behind my face. Page 108 and 109, 6 through 54, every other even. As always, if you have questions, concerns, thoughts, or ideas, make sure you guys are reaching out and asking for help. Let me know so I can give you the assistance that you need. That's all I got for you today, so have a fantastic day.